Hi, how can we solve a task of detecting a specific object, like a horse race, and we don't have a dataset? How can we accomplish this type of task? So in this tutorial we will learn how to detect objects when you don't have a dataset. Before we start any coding, let's explain the target of this tutorial. Basically the major change is that we don't have any dataset. And of course we don't have any annotations for this dataset. All we have is three videos, the videos of horse races. Let's open one of the videos. Basically what we need is to grab the frames of these videos and annotate automatically the horses out of these videos. Let's open another video, and this is the second video. Once again you can see horse race with a lot of persons and a lot of horses, and what we are going to do is to extract the frames out of the videos and do an automatic annotation of those horses, and then we have the ability to train it. And after we finish the train, we go to a different subfolder called test videos, and we would like to run this test video and do a detection on the fly and display the horses on these test videos. So let's see the result. As you can see, this is our test video, and I'm running an inference on the fly and detecting my classes, which are horse racing, using my model that was trained over a dataset that was created automatically. So let's start with tutorial and starting with the installation part. So the installation is based on YOLO v8 8.1, and also we have to install another relevant Python library named AutoDistill. So first of all, let's create a new conda environment. Let's name it AutoDistill, and it will be based on Python 3.8. Then we will of course activate this conda environment, and next we have to install a PyTorch. But in order to choose the relevant version, you should understand and look for your relevant CUDA version. So if you click this command nvcc ---- version, you will discover what is your CUDA version. Mine is 11.8. So then go to the PyTorch website and look for the relevant version for your CUDA version. I decided to install a PyTorch 2.1.1, and this is the full command to install the PyTorch library. Then you should install the YOLO v8.1, so this is the command, and of course we have to install the supervision and install this version 0.9.0, so we will be on the same page. Then install AutoDistill and another library, AutoDistill grounding 0. These both library has the ability to do an automatic annotation. Also, we would like to install the sklearn and RoboFlow. Some functions objects will help us during the training. As for the videos, I will also leave a link for this source data that contains the source videos and the test videos as well, so you can download it and do the tutorial with the same data. Let's start with generating and creating our dataset and annotation. So let's go to our library, our folder, and let's generate a new and fresh subfolder, and we'll name it all images. this subfolder contains all the images that we are going to extract out of our one of the source videos. So let's create a new and fresh Python file. Let's name it step number 1, extract frames from a video. Let's copy the path for our video. So the path points to the directory containing the horse races videos, and let's change the slashes, of course. So this is the pull path for all the videos, and let's create another path named image dir path, and this would be our target path. This is an empty subfolder that we just created, and all the images will be stored in this path. Now let's create a frame stride. The frame stride controls how frequently frames are extracted from the video. A value of 10 means every 10 frame is selected, reducing the total number of images but still capturing enough variation. Next, we will import the Supervision, which is a powerful library for managing object detection tasks, and the TQDM. It will help us to display a progress bar. Then we will use the sv.list files with extensions function to list all the videos in the video dir path directory. And this function filters the files with the specific extensions such as .mov or .mp4, ensuring we only process supported video format. And let's print the list of those videos. As you can see, we have 3 videos with the full path. Now we'll define an image numerator that it will help us to label and count all the extracted frames as they are saved to the disk. Then we will loop over each video file path. For every video found, we extract its name for labeling the frames, and this loop processes each video, ensuring we handle multiple videos. And then we extracting the stem of the video file, which essentially the file name without its extension, and this will be used as a prefix for naming the extracted image files. Okay. Now we create an image sync instance using the image dir path and the image name pattern defined earlier. Image syncs manage the savings of frame to disk. It's automatically save frame using the naming convention we specified. Now we generate frames from the video file. We use the get video frame generator to extract frames. Using the frame stride, we skip frames and reduce the number of images being extracted. We increment the image numerator to keep track on how many frames we've extracted so far. And we print the current image number to track progress during the extraction process. And finally, we save the extracted frames as an image file using the image sync instance. And now, as you can see, we are extracting the videos, and also we go to the all images folder. As you can see, this contains the results of all the images being extracted so far. Let's wait a few more seconds, and I believe that we are ready to jump to the end of this process. As you can see, more than 2,000 images. Let's wait a few more seconds, and that's it. 2,706 images, and here are all the images. Here you can see some sample images. Let's see some more. I think we can go to the next Python file, which is displaying some let's say random images and see that everything seems okay. So we will start with the importing once again the supervision library. Let's copy the result path where we store all the images, and next we will use the list files with extension function to list all the images in the image.dir path directory. Once again, this function filters for image files with extensions such as .png and .jpg, ensuring only supported images are selected. Then we will print the total number of images found in this directory. Let's run it. Great. It's the same amount. Now let's define a sample size that defines how many images we want to select for displaying in the grid. We also define the grid layout with a sample grid size, which specifies as 4x4 grid, meaning we will show 16 images. Now we will import OpenCV for computer vision task, and we will create a list of titles for the images, which are simply the file names without their extension. These titles will be used as labels in the grid. We will use the imread function in order to load those 16 images into our memory, and this ensures we have the image data ready for display in our grid in one shot. And finally, we use the sv.plotImages grid function to display the images in a grid layout. We pass in the images, title, grid size, and plot size to visualize the selected images as a 4x4 grid. Let's run it. Great. As you can see, 16 images. These are the first 16 images. Everything seems okay. Now let's continue the important part, which is automatic dataset generation, labeling and generation. So let's create a folder for that. Let's name it Dataset. Now we will create a new Python file that will be step number 3, auto labeling. So we will start with importing the caption ontology class from the auto steal detection module, and this is used to map object labels to specific classes we want to detect during object detection task. Next, we'll define the ontology for our task. The ontology is a dictionary where the keys represent variations of labels that may appear in our dataset, and the values are the corresponding class labels. In our case, we are focusing on detecting different forms of horse or horse race. As you can see, we are adding 4 types of horse race text. Of course, you can add more, and then the result will be more accuracy and detect more classes. But for our tutorial, we will focus on 4 different labels. Then we will copy the path for all our images extracted in our previous coding, and we will also define a dataset dir path, which is the directory where all our labeled dataset will be stored after running this model. Next, we will define box thresholds and text thresholds. Those are controls the confidence level for detecting bounding box or detecting the level of associated text label for our objects. Now we're importing GroundDino, a pre-trained model available through our auto-steal library. This model is used to automatically generate annotations for our dataset. Then we are initialize the GroundDino model with the defined ontology and set the box and text thresholds to control the accuracy of our model predictions. And finally, we use the base model to label the images in our image dir path directory. The model will annotate the images and save the results in the dataset _dir path. And we also specify the extensions of .png to ensure that the model only processes PNG files, PNG images basically. So let's wait a few more seconds, and as you can see, it's going to run through 2,706 images. Let's jump directly to the end of this process. So the process has finished. As you can see, he ran through 2,706 images. All the images were stored in this subfolder, and the target was, if you go up here, was to put the results here in the dataset subfolder. So let's watch the dataset subfolder. Let's go inside, and now as you can see, we have train folder and validation folder. Let's open the train folder, and as you can see, this structure is a structure of the YOLO images and labels. And let's open the images subfolder, and now as you can see, all the images that were extracted earlier, you can see it here one by one, and for each of those images this process tried to do an automatic annotation. So let's see the results. Let's go back and let's open the first image, and as you can see, the first image is a black image. So if we go to the label subdirectory and open the first label, now as you can see, it's empty. It didn't detected any automatic annotation. But let's go let's move forward, and let's open, for example, let's open this one. As you can see in this image, we have horses and people, and we tried in this code to discover horses or horse races. So let's close this one and let's open the label number 47. Here is 47, and now as you can see, we have automatic annotation for class number 0, for class number 1, for class number 2, and class number 3. So what are those classes? Basically, we defined it here in this code, and if we go back to our result folder, we can also open this data YAML, and you can see that we have 4 classes. Class number 0 is horse, class number 1 is horse, and 2 is horse in a race, and horse racing. So basically in this particular image, he managed, let's go back to the result, he managed to detect all the 4 objects, horse, horse race, and etc. And if we try to display this image with the annotation, we can probably see the bounding box around this automatic detection. So I believe that the next step would be displaying the result, so it will give us the ability to understand how well was this automatic annotation. So let's continue to the next step, which is displaying the result before the training. So now let's display the results. We would like to display some of the images with the annotations, and let's create a new Python file. It will be step number 3. I believe it should be 4. We will fix it later. We will start with importing the required libraries, and then we will define the label names that correspond to the classes we have in our dataset, and these labels are used when displaying the annotations on the images. So we basically created four types of classes. So let's copy those classes and just arrange it in our label names list. So it's horse race, this would be the first one, horse in a race, and horse racing, four classes from 0 to 3. Then we'll define a get annotation function that reads annotation files in a YOLO format. Each annotation file contains information about the bounding box around the object in an image. We extract the label and bounding box coordinates from each line and return them as a list of annotations. Great, so here we are reading the annotations and creating an empty list. And now we will add those annotations, and basically the label, the coordinates, we will store everything on our annotations list. Let's return the results. Great. Now let's create another function named put annotations in image function. This takes an image and its annotations and then draw the bounding boxes and the labels on the image. We convert the YOLO bounding box coordinates to pixel coordinates before drawing the rectangles and the labels over the image. So now we are running through all the annotations, extracting the label and the coordinates. We print the results. We will convert the value to a text. For example, 0 is horse text, number 1 is a horse, number 2 is horse in a race, and number 3 is horse racing. We would like to see the labels. And now we are converting the YOLO coordinates to pixel coordinates in order to display it and display the rectangle on our image. Next, we will use the rectangle OpenCV function in order to display the rectangle over the object. So we are sending several arguments: the image, the position for rectangle, a color, and the thickness of the rectangle. Then we will display the label above the bounding box. Let's put it 5 pixels above our rectangle. We will use a font, choose a font, how thick is the font, and a color for the font. And let's return this image. Now we will create another function, display random images. The display random images function selects a specified number of random images from a folder and displays them with their annotations. So the target is to read the images, apply the annotations, and then show the result image with the bounding box and labels. run a for loop for over the selected images, load the image, load the specific image each time. Next we will get the corresponding label file for the image, which contains the annotations. Let's read the annotations from the label file using the function that we already created. Next, we will overlay the annotations on the image. Once again, we will use the put annotations in image, the function that we created earlier. And now let's display the image. Each time we will display one selected image. We will display the title of the image will be the numerator number inside our loop. Let's define the path for our images, and another variable will be a path for our labels, and the number of images each time. Let's choose the value of 8 random images each time. And let's run the main function, which is display random images. We will send all the relevant arguments, which are the path of the images, number of images, and the label folder. And I believe we are ready to run. I have to fix it. This should be wait key as a function. Also, the return is not in the right position. Okay, so let's run it and see the results. Okay, that is the first random image. As you can see, the automatic labeling, the automatic annotation discovered this horse as a horse, and it's discovered the second horse as a horse racing. Okay, so we have several categories which are similar for us, but the process, the automatic labeling, label each of them as different category. It's not really important, but as for now, as you can see, we have discovered both images. Let's go for the next image. We click a button. As you can see here, there is no horse. So this image is part of the video, and also the automatic annotation didn't find any horse in this image. So that is great. Let's continue. In this image, you can see that it detected this one as a horse racing and this one as a horse, and here it detected several annotations on the same object as horse racing. And let's see, this image detected only this one as a horse racing. Maybe here it had some difficulties because every horses are let's say seems a little bit merged one to each other in the image, so it was maybe for the model a problem to automatic detection, automatic bounding boxes over those three horses together. But it's good enough since we need it for training, so it's detected the horse with a great annotation. Let's continue for the next image. As you can see here, it detected this image as a horse, this object, sorry, as a horse, and this one as well, horse racing, And here we have horse racing, horse racing, great automatic labeling. In this image it detected only this one, and that's it for this first 8 random images. Of course, if I run it again, I will grab out of these 2000 images different random images. But basically we can learn that the automatic process of labeling works very good, and now we have a dataset, a great dataset with annotations that can help us to build a model for horse racing. So now we are ready for the training process. So first of all, we have to create a data.yaml file. This is crucial for the YOLO V8 model. So let's define a train and then the full path for all our train images. So let's copy it from here. Let's change the direction of the slashes, and we have the full path for the train images. Next is the validation images. So it should be val, and then we will copy the valid folder images. So we have to change only this one. So this is the full path for the validation images. Then we have to add all the class names. We have 4 classes, so the NC should be 4, and then we have to put the label names and then all of those 4 names. So our data YAML is ready, and let's continue for the Python code. So let's name it step number 5. It should be 5 train.py, and let's change the previous one. It should be 4. Great. Of course, all the code will be as a link in the video description. Now we will import the YOLO class from the Ultralytics library and define a main function for where all the code training logic will be implemented. Then we will load the YOLO model using the YOLO V8L YAML. L means large, it will be the large model. Next, we will define the path for our custom configuration file, the data YAML, the one that we just created. So let's put the file here and change only the slashes. We also specify the output directory for saving our model checkpoints and experiment results. The project variable sets the base directory, and the next one, experiment, names the specific training run. And this is the experiment. Each time we run the training, it will create another folder for this specific run. It will name my large model, my large model 2, 3, etc. Then we set the batch size to 16. This controls how many images are processed at once during the training. And now we will use the train function in order to train our model using the specific parameters. The data argument points to our custom data.yaml file. We also set the number of epochs to 100, meaning the model will go through the entire dataset 100 times during the training. The project and the experiment names defines where the result will be stored. We also set the batch size, specify the device, which is GPU, for training, and add an early stopping with a patient set of 40 epochs. The image size defines the input size image. The verbose true enables the detailed login, and the val true ensures validation is also performed during the training. And then the main function is called when the script is executed, initializing the training process. We have a syntax error in the image size. It should be imgsz. And let's run it. Let's load the model. And now it's loading the training images. Let's wait a few more seconds. And now it's loading the validation images. Let's wait a few more seconds. And the training has started. So this is the first epoch. You can see the progress. And of course we are not going to wait 100 epochs. It should be several hours. So let's jump to the last step and see the results of the training. After several hours, the training has finished. As you can see, the results is stored here. This is the weights of the last epoch, and this is more important. This is the weights file for the best epoch. And basically, let's go to this library that contain all the results. As you can see here, this is the result for each of the classes. We made a training for these categories: horse race, horse in a race, and horse racing. And most of the values are of the precision about 0.7 or 0.8. I believe it should be a good result. We ran about 100 epoch, and may I remind you that we had an early stopping after 40 epochs, so I think we could add more epochs and wait more time if you would like that the accuracy would be better. But I think it's good enough that we can continue and try the prediction. And first of all, let's go to this results folder. So let's open. This is our dataset, and let's open here dataset and then checkpoints and then my large model. So everything was stored here. First of all, let's open this file results.png, and as you can see, if we are looking here at the train and the class losses, we can see a very good line that goes down, and that means that we have a good results of our model. Let's also follow this precision. Basically here it should go up. There are a lot of spikes, but the general idea it goes up. And let's also open here. There are images from the validation data. For example, let's open this one, validation batch 1 prediction. And here, as you can see, in this image it predicted this horse as a category of horse racing, and here a detected this horse, and here detected all these horses, and here it didn't detect anything since we don't have any horses in this image. In this specific image you have a lot of predictions. You can see horse racing, horse race, and also the value of the prediction is also a good one, a good value. So let's continue to the next step. The next step would be taking one of our test videos. Let's go back to the dataset. Let's go to the source data, and let's take one of these videos from the test videos. So these are our test videos. Let's choose one of those videos. Let's take this one, video number 12. And as you can see, it's in horse racing. And what we are going to do next is use our model, the weights of our model, the one that we trained, and run the video, grab the frames, run it through our as an inference through our model, and predict the horses that appears on this video. So we are expecting to see the same video with bounding boxes that detects those horse race. So let's start. So now let's run a prediction over one of our test videos. So we would like to run a video and do an inference in real time and predict those horses. So we will start with importing the necessary libraries. We set up the path for the video files and the pre-trained YOLO model. So this is the path for our videos, and let's choose one of those videos. Let's choose video 12. This is the name of the video 12.mp4. Now we will define the path for our weights for our model. The weights are stored in the checkpoint subfolder, and beneath that the my large model, beneath that weights, and beneath that path.pt. So this is the full path for our trained model. And next we will load the YOLO model using the trained weights from our specific path, and we will also set a threshold of 0.25 to filter out low confidence detection. Now we are creating a video capture object to read frames from the video file, and this will allow us to process the video frame by frame. Now we enter a loop to read and display the video frames one by one, and the loop will continue until there are no more frames to read. Now we check if the frame has been successfully read from the video. If not, we break out the loop, indicating that the video has ended. Next, we pass the current frame to the YOLO model for object detection. The model returns the detection results, which include bounding boxes, scores, and class IDs. We loop through the detected object and extract the bounding box coordinate, the detection score, and the class ID for each object. If the detection score exceeds the thresholds, we will draw a bounding box around the object. We also add a label with the object class name above the bounding box. So let's grab the coordinates, let's convert it to integer values, and then we are ready to use the rectangle function and display the bounding box around each of those detected objects. Once again, we use a color, we choose a color, we choose the thickness of the rectangle, and same for the label of this class. Let's put the label about 10 pixels above the rectangle. After processing the frame, we display it in a window titled, let's name it video, and this window will show the video with bounding box and labels overlaid on the detected object. We set up a key press check. If a Q key is pressed, we exit the loop and stop displaying the video. And once the video has finished or the Q key is pressed, then we will release the video capture object and close all the OpenCV windows to clean up. And I believe that we are ready to run it. And let's see the horses. And you can see the green detected boxes. Here are 2 of them. Great. Thank you very much. I hope you enjoyed this tutorial. You are most welcome to subscribe my channel. Bye bye.